If you take a standard carbon chain and replace one of its predictable hydrogen atoms with a highly reactive halogen like chlorine, bromine, or iodine, the entire molecule changes. You've just created a haloalkane. These molecules act as versatile intermediates. Because halogens are easily swapped out for other groups, they allow chemists to assemble the complex carbon skeletons required for modern pharmaceuticals at an industrial scale. Beyond the lab, they are essential to thermodynamics. For decades, haloalkanes like Freon were the primary cooling agents used in nearly every household appliance. However, halogens are aggressive elements. Simply attaching one to a chain produces unpredictable results, because the chemical properties shift based on the exact spot where the halogen lands. To manage this volatility, chemists use a three-tiered sorting algorithm to map molecular structures and predict how they will behave in a reaction. First, we count the halogens, splitting our tree into mono, di, and polyhaloalkanes. While mono and poly are straightforward, dihaloalkanes, with exactly 2 halogens, require checking their placement. If both halogens share the same carbon, it's geminal. On neighboring carbons, it's vicinal. To see the deeper rules of molecular geometry, we're going to follow the mono branch downward into the next tier. Counting atoms is only the first step. The physical network surrounding those atoms is what truly dictates the molecule's reactivity. Moving down the monohaloalkane branch, we identify the anchor carbon, the specific atom that the halogen is directly plugged into. We classify the anchor by connectivity. Attached to one other carbon, it's a primary classification. 2 connections is secondary. 3 is tertiary, where the anchor is surrounded by carbon groups. This physical crowd around the anchor is called steric hindrance. Steric hindrance acts as a physical shield, determining how easily an outside molecule can reach the anchor to trigger a chemical change. The final layer of our algorithm's classification depends entirely on the invisible, underlying geometry of the electron bonds themselves. In the sp3 branch, the anchor uses only single bonds, categorized as alkyl, allylic, or benzylic, based on proximity to double bonds or rings. Conversely, the sp2 branch features an anchor within a double bond, resulting in vinylic or haloaryne classifications. This fundamental geometry locks in the molecule's final identity, completing its profile in the sorting algorithm. Combining halogen count, degree, and hybridization creates a complete structural map. Knowing a molecule's tier 2 degree predicts its reaction pathway, SN1 or SN2. Tier 3 hybridization predicts bond stability, since an sp2 bond is much stronger than an sp3. This system is a predictive tool. It gives scientists the precise vocabulary to control chemical outcomes and design the specialized materials we use every day.
Look at a standard hydrocarbon. It is perfectly balanced, incredibly stable, and for a chemist trying to build something new, it is a dead end. To manufacture the vast array of medicines, plastics, and industrial materials we rely on, you can't just leave that molecule alone. You have to intentionally break its equilibrium. The most effective way to do this is a precise molecular swap. If you remove a single hydrogen atom and replace it with a halogen, fluorine, chlorine, bromine, or iodine, you completely change the molecule's behavior. If you make this swap on a straight carbon chain, you get a haloalkane. If you swap it onto an aromatic ring, like benzene, you create a haloaryne. This single atomic chain acts as a versatile bridge, providing the reactive starting point needed to synthesize more complex families like alcohols, ethers, and aldehydes. Because this halogen swap dictates exactly how the molecule will behave next, chemists need a precise way to map the new architecture. First, we count. 1 halogen is a monohalogenated structure. 2 make a distructure. 3 or more a polycategory. Placement also matters. If 2 halogens share the exact same carbon atom, they form a geminal structure. If they're on adjacent carbons, it's a vicinal structure. We also track the host carbon itself. By counting how many other carbons are directly attached to the one holding our halogen, we classify the molecule as primary, secondary, or tertiary, written as 1, 2, or 3 degrees. The exact physical location of that halogen determines the specific ways this molecule can be attacked, broken apart, and rebuilt in a laboratory. To see exactly why this upgraded molecule is so reactive, we need to zoom into the gap between the carbon and the new halogen.
Halogens have electronegativity. They don't steal the carbon's electron completely. Instead, the halogen relentlessly pulls the shared electron cloud toward itself. This tug-of-war creates a polar covalent bond. The halogen takes a partial negative charge, and the carbon gets a partial positive charge. There is a standard rule as you move down the periodic table from fluorine to iodine. The atoms get physically larger, the length of the bond increases, and the strength of that bond predictably drops. This chart shows the dipole moments, the overall measure of that electrical tension for the different halogens. You would expect fluorine to have the highest dipole moment, but look at chlorine. Its bar unexpectedly spikes higher than fluorine's. The math explains this. Dipole moment is calculated by multiplying charge by physical distance. Fluorine has a massive charge, but its atomic radius is so small that the lack of distance drags the equation down. It is exactly this internal electrical tension, the permanent imbalance of charges across the bond, that makes haloalkanes perfect targets for other chemicals to attack. Knowing the physics of the bond is one thing. Synthesizing these molecules effectively in a laboratory is another. Exposing an alkane to chlorine gas triggers free radical halogenation. Halogens attack continuously, creating a chaotic mixture of byproducts. A cleaner approach? React an alcohol with thionyl chloride. This produces your target haloalkane, while the gaseous byproducts simply evaporate and float away. But if you're starting with an alkene, a carbon chain that contains a double bond, you have to follow a specific guideline called Markovnikov's rule. When you break that double bond using a hydrogen halide, you have one hydrogen atom and one halogen atom to distribute. Markovnikov's rule dictates that the hydrogen automatically magnetizes to the carbon atom that already holds the most hydrogens. This happens because breaking the double bond creates a temporary intermediate state called a carbocation. Nature simply routes the atoms in the direction that forms the most stable intermediate structure. Understanding these underlying architectural rules allows us to see the logic behind the reactions, moving past the need to memorize thousands of individual equations. Grasping how and why the carbon-halogen bond behaves as it does provides the blueprint needed to navigate the broader landscape of organic chemistry. Pure hydrocarbons, the chemical foundation of fossil fuels, are incredibly stubborn. Their atomic structures are perfectly balanced and tightly bound, causing them to resist reacting with most other substances. In their raw form, these molecules are a chemical dead end. To alter these inert structures, chemists must create a point of vulnerability. They do this by introducing an aggressive chemical infiltrator, a halogen, such as chlorine or bromine. Removing a hydrogen atom from a hydrocarbon and snapping a halogen into the vacancy creates a haloalkane. This connection is a polar covalent bond. Electronegative halogens pull the shared electron cloud, creating a permanent electrical imbalance, a partial negative halogen and a partial positive carbon. This internal electrical tension transforms the molecule. By establishing this specific polar weak point, chemists turn a previously unreactive hydrocarbon into a viable starting point for complex synthesis. Inserting that halogen requires precise control, but the earliest methods were blunt. Free radical halogenation involves saturating alkanes with halogens and blasting the mixture with intense ultraviolet light. The problem is that the reaction is indiscriminate. Once the UV light breaks the halogen bonds, they don't stop after replacing one hydrogen. They relentlessly attack the molecule, replacing multiple hydrogens in a chaotic chain reaction. This produces a mixture of different compounds that are nearly impossible to separate into pure substances. For a chemist who needs a specific, isolated molecule, this method is too unpredictable for precise work. To gain better control, chemists often use an alternative, adding a hydrogen halide across a carbon-to-carbon double bond. When this double bond splits to accept new atoms, the placement is governed by a physical law known as Markovnikov's rule. The rule dictates that the incoming hydrogen atom will attach to the carbon that already has the highest number of hydrogens. This leaves the adjacent carbon open for the halogen, resulting in a predictable, stable molecular structure. Successful synthesis relies on exploiting these inherent physical biases. By following the molecule's internal logic, chemists can place a halogen at a specific coordinate, rather than relying on brute force. Another pathway to avoid the chaos of alkanes is to start with alcohols. But because alcohols behave differently depending on their structure, chemists must first determine if the molecule is a primary, secondary, or tertiary degree. The diagnostic solution is the Lucas reagent test. By mixing the alcohol with zinc chloride and hydrochloric acid, the specific time it takes for the liquid to react reveals the degree of the alcohol. Tertiary alcohols react instantly, turning the liquid opaque. Secondary alcohols take roughly 5 to 10 minutes to show any change, while primary alcohols stay perfectly clear at room temperature. Once the alcohol is identified, it can be converted using what is widely considered the most efficient reaction for this purpose, thionyl chloride. When thionyl chloride reacts with the alcohol, the unwanted byproducts, sulfur dioxide and hydrogen chloride, are naturally produced as gases. Because these byproducts simply bubble out of the solution and escape into the air, the reaction requires no extra purification steps. It is a self-refining process that leaves behind a pure, high-yield haloalkane. Even with these established rules, the periodic table presents a specific anomaly when dealing with the smallest of the halogens. Generally, as you move down the halogen group from fluorine to iodine, the atoms get larger and the bonds to carbon get longer and weaker. This chart shows the dipole moment, or the measure of electrical imbalance in the bond. The trend should decrease as atoms get larger, but fluorine shows a lower dipole moment than chlorine. This occurs because fluorine is uniquely compact. Despite its immense electrical charge, the physical distance between nuclei is so short it reduces the overall dipole value. These atomic measurements are more than just data points. They define the reactivity that makes the haloalkane so valuable to global industry. Because the carbon-halogen bond is polar and relatively easy to break, it acts as a universal mounting point. Chemists can swap the halogen for a hydroxyl group to create alcohols, or nitrogen to form amines. This single substitution pathway provides the foundation for modern manufacturing, from the synthesis of PVC plastics for infrastructure to the creation of the complex molecular rings found in anti-inflammatory drugs and antibiotics. By mastering the controlled disruption of this one bond, humanity gains the ability to assemble the materials that define the modern age.
At the molecular level, chemical substitution occurs in high-energy environments. Structures are constantly colliding, breaking, and forming bonds to reach a more stable state. Within an alkane framework, the process targets a central carbon atom. Attached to this carbon is a halogen atom. We categorize this as the leaving group, because it is the component being replaced during the reaction. The reactive agent seeking to bond with the carbon is the nucleophile. The fundamental goal is simple: exchange the halogen for the nucleophile. While the objective is constant, the physical path the atoms take depends entirely on the architecture surrounding that central carbon. We can see this divergence by comparing a primary carbon on the left with a tertiary carbon on the right. The primary carbon is attached to only one alkyl group. With only small hydrogen atoms occupying the other bonds, the central carbon is relatively exposed. The tertiary carbon is surrounded by 3 bulky alkyl groups. These substituents physically encase the central atom. In an SN2 reaction, a single-step substitution, the exposed primary carbon reacts rapidly. However, the tertiary carbon's reaction rate for this same mechanism drops to 0. We see the opposite trend in an SN1 reaction, which involves 2 steps. The primary carbon fails to react, while the tertiary carbon executes this pathway efficiently. While the primary carbon completes its substitution in a single motion, the crowded tertiary carbon follows a multi-step sequence to achieve the same result. This preference for the SN1 pathway is a requirement dictated by the specific interaction between steric hindrance and carbocation stability. A single-step SN2 substitution relies on a specific geometrical alignment. To bond with the carbon, the nucleophile must perform a backside attack at exactly 180 degrees, opposite the leaving halogen. When we look at the tertiary haloalkane using van der Waals radii, we see the actual spatial footprint of the 3 methyl groups. The volume these groups occupy creates a physical barrier known as steric hindrance. As a nucleophile attempts the 180-degree backside attack, it enters the space occupied by these alkyl groups. The electron cloud of the nucleophile begins to repel the electron clouds of the 3 surrounding groups. This repulsion prevents the nucleophile from reaching the central carbon. The physical trajectory is blocked before a new bond can even begin to form. Steric hindrance renders the SN2 pathway physically impossible for a tertiary carbon, forcing the system to find an alternative route. Because the direct attack is blocked, substitution can only begin if the leaving group detaches on its own.
When the halogen bond snaps, it takes both bonding electrons with it, leaving the carbon framework incomplete. The result is a carbocation, an intermediate state where the central carbon carries a full positive charge. To minimize electronic strain, the three alkyl groups repel one another into a single plane, shifting the framework from a 3D tetrahedron to a flat 2D geometry. Maintaining a positive charge on a single carbon atom is typically too unstable for the molecule to survive. However, the tertiary structure utilizes the inductive effect, where the three surrounding alkyl groups shift their electron density toward the center. This inward donation of negative charge stabilizes the positive center, providing the electronic scaffolding necessary for the intermediate to exist. The same bulky groups that physically block the SN2 attack provide the electronic stabilization required for the molecule to proceed through the SN1 pathway. This stabilized flat intermediate is known as a trigonal planar carbocation. Because the structure is flat, an unoccupied p orbital extends above and below the plane. The nucleophile returns. With the steric barrier gone, it can attack from the top or bottom, making either path equally likely. This trigonal planar geometry creates a perfectly split probability, removing the strict 180-degree restriction found in the SN2 mechanism. If the nucleophile bonds from the top, it produces a molecule with one specific spatial orientation. An attack from the bottom produces its exact mirror image. The result is a perfect 50-50 split of mirrored molecules, a racemic mixture. This contrasts with SN2, which always produces a single inverted orientation. Detecting this mixture provides empirical evidence that the reaction proceeded through a flat intermediate. The tertiary carbon is governed by its physical volume, which creates a blockade against concerted attacks. Simultaneously, it is enabled by its internal electronics, which allow it to survive a multi-step sequence. Deliberate pacing. The tertiary carbon's preference for SN1 is the result of its molecular architecture. It follows the only physical path that its structure allows.
If you strip away everything else, the universe is mostly empty space and a vast amount of pure hydrogen and helium. But billions of years ago, supergiant stars forced simple elements to fuse together, created new, heavier elements, and exploded them across the universe. Left to drift, these elements are governed by a strict rule of physics. All matter is constantly trying to minimize its combined energy. To reach that lower energy state, these atoms are forced to interact. They bump into each other, stealing or sharing electrons to balance themselves out. That microscopic drive for stability is the engine of chemistry. Early humans harnessed these exact reactions when they discovered fire. We used the energy of that reaction to cook food, to harden clay, and extract metal from ores. By learning how to control the ways matter interacts, we took the scattered debris of dead stars and built modern civilization. This chart organizes all those different types of atoms, the chemical elements. Elements in each column share similar properties, dictated by their distinct structures. Inside an atom is a nucleus of protons and neutrons, but chemistry is dictated by its outer shell of orbiting electrons. Apply heat or pressure, and electrons alter their behavior. Atoms lock into solid crystals, flow as liquids, or are ripped apart into plasma. Tracking how atoms interact at a quantum level is incredibly difficult. Simulating anything more complicated than hydrogen requires advanced computer science and intense mathematical modeling. By mapping out those physical and quantum rules, we can predict exactly when and how a substance will shift its form. When atoms do join together into molecules, they form chemical compounds with entirely new properties. Take highly explosive hydrogen, combine it with combustible oxygen, and get perfectly stable liquid water. But every chemical reaction is bound by strict physical boundaries. The conservation of mass and energy dictates that nothing is ever created or destroyed in a reaction. It only changes form. A common way this transformation happens is through an oxidation-reduction reaction, or redox. This is a direct exchange where electrons are actively stolen from one reactant and given to another. To observe these microscopic transfers, analytical chemists developed an immense array of physical techniques. By separating compounds based on their mass or exact evaporation temperatures, they can measure exactly what a sample is made of. Measuring and controlling these invisible energy transfers gives us the precise instructions needed to manipulate our physical environment.
In the field of inorganic chemistry, we manipulate non-living, mostly man-made materials. This allows us to synthesize extreme-strength alloys, industrial catalysts, and high-temperature superconductors. Then there is organic chemistry. This is an entire kingdom of science built almost exclusively around the carbon atom and the complex bonds it can form. Manipulating carbon structures leaves a massive industrial footprint. We use it to synthesize agricultural fertilizers, formulate chemical lubricants, and mass-produce synthetic polymers and plastics. Mastering both of these areas, the inert minerals and the carbon-rich molecules, gives us the tools to produce everything from heavy fuels to precision pharmaceuticals. The most complex application of these physical rules happens inside living organisms. Biochemistry is the study of the chemical processes that drive biological life. That same atomic drive to minimize energy scales up. Simple elements combine to build massive biomolecules: carbohydrates for energy storage, lipids for fats, complex chains of proteins, and the nucleic acids that form your genetic code. Mapping these biological structures directly advanced human medicine. It allowed us to accurately diagnose diseases, map genetics, and successfully perform complex tissue and organ transplants. Even the act of thinking is driven by these same microscopic processes. The brain depends on a constant chemical flow, oxygen being passed through the blood and sugars being metabolized to sustain the neural activity that generates consciousness. Chemistry spans the distance from a single drifting atom to the trillions of reactions occurring inside you right now. It is the physical framework that allows simple matter to assemble into the complexity of human life.
When a carbon atom collides with a halogen, they lock into a specific geometric relationship. The physical forces binding them in this moment dictate the behavior of thousands of different compounds. This exact carbon-halogen architecture repeats across a massive array of organic molecules, from consumer refrigerants to complex pharmaceuticals. Organic chemistry operates through the same strict physical laws that govern any other mechanical system. Analysis of 3 specific properties of this bond: its length, its required dissociation energy, and its orbital hybridization, provides a map of how a molecule will behave physically and chemically. We can apply this analysis to 2 major classes of molecules: aliphatic haloalkanes, which form straight or branched chains, and aromatic haloarynes, built on closed benzene rings. Whether a compound forms a volatile gas or a dense solid, or whether it yields to a chemical attack or repels it, is determined entirely by its subatomic geometry. This diagram compares the 4 primary halogens: fluorine, chlorine, bromine, and iodine. Fluorine is compact, iodine is massive. As the atomic radius increases, the bond length stretches. A longer bond is weaker. Thus, bond dissociation energy decreases, moving from fluorine down to iodine. Atomic mass directly controls external physical states. The heavier the attached halogen, the stronger the intermolecular forces, which requires higher temperatures to boil the substance. But mass is only part of the equation. This comparison shows a long-chain haloalkane next to a highly branched isomer with the same chemical formula. The branched structure physically reduces the molecule's overall surface area. With less surface area, the van der Waals forces between the molecules weaken. Consequently, branched isomers have noticeably lower boiling points than their straight-chain counterparts. 3D shape directly alters macrophysical states. We see a related geometric effect in the melting points of dihalobenzenes. Molecules with halogens positioned exactly opposite each other on the ring, para-isomers, melt at higher temperatures than their ortho and meta variations. The reason is strict crystalline symmetry. The linear, balanced structure of a para-isomer allows the molecules to pack tightly into a rigid crystal lattice, requiring more thermal energy to break apart. A compound's physical state, as a gas, liquid, or solid, is a direct calculation of its atomic mass, its exposed surface area, and its crystalline symmetry. This split screen compares the baseline structure of our 2 main classes. On the left, the haloalkane features an sp3 hybridized carbon, bound by a standard single signal bond. On the right, the haloaryne is built on an sp2 hybridized carbon within a benzene ring. The sp3 carbon's single bonds are highly polarized, creating a positive charge targeted for chemical substitution. The haloaryne has a built-in defense. The halogen's lone electron pairs delocalize,
flowing directly into the continuous pi electron system of the benzene ring. This sharing of electrons across the structure is resonance. Resonance changes the physical nature of the CX bond. Because of this resonance, the carbon-halogen connection develops partial double bond character. The bond visibly shortens and thickens, making it more rigid and chemically robust. This reinforced bond physically locks the halogen in place. Nucleophiles, molecules seeking to attack a positive charge and replace the halogen, cannot easily break this shortened bond. The sp2 hybridization and resulting resonance act as molecular armor. This orbital arrangement effectively armors the molecule, preventing the bond breaks that aliphatic chains easily undergo. When aliphatic chains undergo substitution, they are attacked by a nucleophile, an electron-rich molecule seeking to bond with the positively charged carbon and replace the halogen. These space-filling models illustrate how a nucleophile's success depends on steric hindrance, the physical crowding around the target carbon. Moving from left to right, notice the dense wall of bulky methyl groups crowding the tertiary carbon. The primary carbon on the left lacks this crowding. This allows the nucleophile to execute a direct backside attack. In a single bimolecular step known as the SN2 pathway, the nucleophile strikes the back of the carbon, instantly popping the halogen off the front. Because it attaches from the opposite side, this strike causes an inversion of configuration, flipping the geometry like a wind-blown umbrella. But on the tertiary carbon, the nucleophile attempts the same backside attack and bounces off the dense wall of methyl groups. The path is geometrically blocked. This blockade forces the tertiary molecule down a different route, the SN1 pathway, which requires two distinct steps. First, the halogen must detach entirely on its own. This leaves behind an exposed, flat carbocation intermediate. Only then can the nucleophile attack. Because the intermediate is planar, the nucleophile can bond from either side, resulting in a mixed geometric product called a racemate. Molecules do not choose between the SN1 and SN2 pathways. The reaction mechanism is strictly dictated by the physical bulk of the surrounding atoms. Nucleophiles are not the only threat to these molecules. If exposed to an alcoholic base, the reagent doesn't substitute itself into the structure. It strips atoms away in a process called beta elimination. The base removes a hydrogen atom from a neighboring, or beta, carbon. This forces the halogen to detach, and the carbon atoms form a double bond to satisfy their electron requirements. This creates a problem with multiple beta carbons. Which hydrogen does the base steal? Following Zaitsev's rule, the reaction targets the carbon with fewer hydrogens. This geometric preference yields the most highly substituted and therefore stable carbon-carbon double bond. We see a similar thermodynamic preference in haloarynes. While their partial double bonds repel nucleophiles, the dense electron-rich pi cloud above and below the benzene ring makes them attractive to positive electrophiles. When an electrophile attacks, the halogen already on the ring acts as a traffic director. Its resonance pushes electron density toward the ortho and para positions on the ring, steering the incoming group exactly where to attach. Whether an aliphatic chain forms a double bond via elimination, or a benzene ring accepts a new group at a specific coordinate, the chemical outcome follows the path of least electrostatic resistance. When we multiply these physical properties by attaching several halogens to a single carbon framework, we create polyhalogen compounds. The consequences of their subatomic geometry impact human history and the global environment. Look at this early polyhalogen, chloroform. The heavy chlorine atoms gave it specific anesthetic properties used in early medicine. However, it reacts with oxygen, slowly degrading into highly toxic phosgene gas, making it dangerous to store. Compare that instability to the strength of the carbon-fluorine bond. By combining chlorine and fluorine on carbon centers, chemists engineered chlorofluorocarbons, or freons. Their stable geometry made them ideal, non-toxic propellants for aerosols and refrigerants, resulting in their mass production and daily use. These satellite readings show a massive, expanding void in the total ozone over Antarctica between 1985 and 1988. Because the carbon-fluorine bond is virtually indestructible in the lower atmosphere, freon molecules survived long enough to reach the stratosphere, where solar radiation broke them apart and allowed the halogens to shred the ozone layer. A similar persistence applies to DDT, a heavily substituted polyhalogen insecticide. Its molecular structure makes it hydrophobic and resistant to metabolism. Instead of breaking down, it bioaccumulated in fat tissues, resulting in severe ecological damage. The same atomic properties that make carbon-halogen bonds useful in industry, extreme stability and specific reactivity, are what turned them into persistent environmental threats when released at scale. This matrix summarizes our model. A primary sp3 carbon dictates an SN2 substitution. A crowded tertiary sp3 carbon forces an SN1 reaction, and an aryl sp2 carbon demands electrophilic substitution. Organic chemistry is the inevitable expression of bond energy, atomic size, and orbital geometry. Once you understand the physical bedrock of the molecule, its behavior, whether in a test tube, a crystal lattice, or the upper atmosphere, is a logical certainty.
Look closely at carbon-based molecules like alkanes or benzene rings. They form the structural foundation of organic chemistry, largely because they are naturally stable and resistant to change. That stability creates a hurdle for synthesis. To build complex, useful materials, we have to attach new pieces to these carbon chains, but they lack the reactive points needed to form a bond. The solution is to strip a hydrogen atom and replace it with a highly reactive halogen, like chlorine or bromine, creating a haloalkane. That halogen provides a reactive site, transforming a stable chain into a molecule that actively binds with new structures. Manipulating these reactive sites requires high precision. Chemists rely on name reactions to dictate exactly how these molecules behave under specific conditions. These reactions provide the operational control required to build specific molecular structures on demand. Certain halogens are difficult to attach directly to a carbon chain. In these cases, chemists first build a basic haloalkane and then perform a precise chemical swap. When the goal is to attach an iodine atom, chemists deploy the Finkelstein reaction. Introduction of sodium iodide in a dry acetone environment allows the sodium to bond with the original halogen. As that bond breaks, it clears the path for the iodine to take its place on the carbon chain. Fluorine poses a different challenge. It reacts so aggressively with carbon that direct attachment is difficult to control, making the Schwarz reaction the preferred method for safe attachment. Instead of a direct approach, the Schwarz reaction utilizes heavy metallic fluorides, like silver fluoride. The silver removes the original halogen, while the fluorine transfers over to the carbon chain in a controlled exchange. By utilizing these exchange methods, chemists can produce specialized alkyl iodides and fluorides that would be difficult to create through direct halogenation. Aromatic benzene rings, or haloarynes, require a different approach. Their closed-loop structure is inherently resistant to the substitution methods used on straight carbon chains. To modify the ring, chemists synthesize a highly reactive intermediate compound known as a diazonium salt. Synthesized at low temperatures, the diazonium salt creates a localized point of instability on the ring, making it receptive to a new halogen atom. Once primed, Sandmeyer and Gattermann reactions deliver the final halogen. Sandmeyer uses a copper salt for the exchange. Gattermann uses copper powder and halogen acid. In both, the diazonium group is displaced, allowing the new halogen to bond. Sometimes the objective is to remove the halogen entirely, to fuse two separate carbon molecules together. This fusion process requires sodium metal suspended in a dry ether environment. In the Wurtz reaction, sodium strips halogens from two straight-chain haloalkanes. The exposed carbon ends immediately bind, forming a longer chain. The Fittig reaction applies this to haloarynes. Sodium removes the halogens and fuses two hexagonal benzene rings directly, creating a biphenyl structure. The Wurtz-Fittig reaction joins distinct carbon structures. By introducing one straight haloalkane and one halobenzene ring, the sodium removes both halogens, allowing the straight chain to graft directly onto the side of the aromatic ring. These methods allow for the expansion of molecular size, connecting isolated carbon fragments into larger frameworks. When we look at these reactions together, we see three distinct operational categories: the swappers, the aromatics, and the welders. Names like Finkelstein, Schwarz, and Wurtz represent specific protocols for the deliberate construction of molecules. Haloalkanes and haloarynes provide the starting materials for advanced organic construction. This type of molecular engineering is the standard for chemical synthesis.
allowing for the production of complex pharmaceuticals and specialized polymers. These reactions form the baseline for chemical manufacturing, enabling the predictable assembly of molecules for use in modern medicine and industry.